Hi everyone, we are presenting PALM, Progress Aware Policy Learning via Affordance Reasoning for Long Horizon Robotic Manipulation, our CVPR 2026 paper. I want to start with the motivation of why long horizon is hard. So vision language action models work on short tasks, but break down on long multi-step manipulation. And we have two failure patterns. The vanilla VLAs map image and instructions straight to action, so no awareness of subtask progress, so they drift across stages. And vision subgoal predictors generate future images as guidance, but depend on predefined subgoals and it can adapt semantically. So neither keeps a long sequence on track. Now, Palm closes both gaps in one unified VLA. The three ideas are that first, we have a unified framework coupling affordance reasoning with progress estimation. And second, we have structured affordance foresight that predicts future interaction cues for context placement and motion. And we also have progress aware reasoning that tracks subtask completion. At the core, Palm uses two learnable query sets, affordance queries that forecast the next interaction, and action progress queries that jointly decode an action and a continuous progress value. And conditioned on predicted future affordance, the policy stays temporally coherent across long sequences. Here's the architecture. Three inputs go in, an instruction encoded by clip, an image encoded by masked autoencoder and a downsampled with a perceiver resampler, and the robot state through an MLP. Um, and a GPT-2 style backbones view system. And on top sits two query sets. The affordance query has four subqueries: global, local, spatial, dynamic. Global identifies a reference object supervised by grounding dyno and SEM. Local predicts a contact likelihood heat map following Glover++. Spatial outputs candidate placement points from spatial VLM and robot point. Dynamic forecast which pixels, gripper, and movable objects will move supervised by CodeTracker. And these are train only. The action progress query conditions on the affordance latent and it feeds a diffusion transformer that decodes an n-step action sequence plus a continuous progress scalar. So in one pass, we have where to act, what to do, and how far along. In our real world setup, we have real hardware, a U-Factory X ARM6 with Gripper G2, and two RealSense D455 cameras, one eye on hand, one eye on base. We fine-tune on 200 in-house demos. The evaluation task is one high-level instruction unfolding into six consecutive pick and place subtasks. For our generalization settings, we have three stress tests. In setting one, we have random relocation. The target's pose is varied. On setting two, we have unseen lining. The scene lining is changed. In setting three, the visual destruction. Extra objects clutter the workplace. So these are the conditions long horizon policies typically collapse under. We compare against VopenVLA and Octo, fine-tuned on the same data, reporting success rates and average length over 20 rollouts. Across all three settings, Palm delivers roughly 2 times long horizon completion. For random relocation, it's 3.05 versus 0.95. For vision destruction, we got a 3.8 versus 1.6, and unseen lining 3.55 versus 1.25. Baselines collapse to zero by the fourth or fifth subtask, and Palm still completes a 60 to 40% of the time. These videos show Palm running the same six-step sequence under the original conditions, then unseen lining, visual destruction, and random localization. So Palm keeps tracking the right object and transitions cleanly between stages. Behavior the baselines don't reproduce. That's Palm, affordance reasoning plus progress animation for reliable long horizon manipulation, and thanks for watching.